We have talked about equipartition theorem. Now, let us talk about another one which is very important. It is called as a Virial theorem, and we will see that how Virial theorem is important both in classical and quantum mechanics, and we will do it from two perspectives. So, one is we will do thermodynamics of gravitating objects, and then we will shift over to statistical mechanics and do these for or derive the Virial theorem for the classical ideal gas and maybe for harmonic oscillator as well. And we will also do a generalization of the canonical ensemble by allowing the systems to exchange particle or the particle numbers to be a variable among them, which is a more realistic scenario than the canonical ensemble. So, let us write down Virial theorem. So, we will have to define what is a virial. This word may be new to you, to at least some of you, and it states basically it tries to find a relationship between average kinetic energy, let us call it as K, and average potential energy V. Okay. And you see that this is quite useful because the total energy is the sum of the kinetic and the potential energies, and if we know the relationship, the average relationship of these K and V, or even in quantum physics, which is known as the expectation value of the kinetic energy and the potential energy, then we know that how the energy is actually distributed between the kinetic and potential energies in a system. And see, these things at least in say for example quantum mechanics, it is not so easy to calculate, because say for example in hydrogen atom, if you want to know the expectation value of the kinetic energy and the potential energy, it is quite difficult, because these are the wave functions that we would need for calculating the expectation values. They are log-square polynomials and some exponentially decaying function, or say for example in harmonic oscillator, it is the Hermite polynomials and a Gaussian. So, a general relationship for the nth eigenfunction, if you have to calculate these expectation values of kinetic and potential energies between the general wave function, it can be quite daunting in terms of its mathematical complexity. So, this straight away gives an example or rather establishes a relationship between K and V. So, let us do it for gravitational bodies. Let us call it gravitational objects, and derive this relation and see that what it gives, or what the was the relationship between average kinetic energy and average potential energy. To do that, we will have to define a variable, but before that let us define the moment of inertia. So, this is moment of inertia, and this all of you are familiar in classical mechanics, and this is equal to I equal to 1 to n for say n point objects. It is R I and you have this square. So, there is a general definition of moment of inertia, all of you are familiar with this, and this is m I into R I dot R I, and I of course goes from 1 to n. So, this is the definition of moment of inertia, and the time derivative of this moment of inertia is called as a virial. So, we will define virial, and there is a slight adjustment that is done to include a factor of 2 in the denominator. So, virial is defined as virial. We will use another symbol for defining virial when we do for this classical gas and so on, or the oscillator, but nevertheless they mean the same thing. We will use symbol like this, or you can use a symbol like this, or they just mean the same thing. So, this is half of di dt is called as the virial. Okay. And we will see that whether you write it in terms of this curly v or you write it in terms of q, and then the final expression for the virial would just be identical in all these cases, which they should be. So, this di dt is equal to sum over I, and there is I from 1 to n, and we have a pi dot ri. Okay. So, because both of them give you a pi dot ri and we have taken a half. So, this factor of 2 goes away and we get a virial equal to pi dot ri, where pi is the momentum of the individual particles. All right. So, then what do we do is for deriving this theorem, we will use the time derivative of this, which is dq dt, which is equal to, so we have a chain rule that needs to be applied, and we have a I equal to 1 to n, and you have a dpi dt dot ri plus pi, plus I equal to 1 to n pi dot vi. Okay. Vi is nothing but dri dt, and if we use Newton's second law, we get Fi is equal to dpi dt. Okay. So, this is will be used on the first term in the right, and we can write down this time derivative of the virial equal to Fi dot ri plus, now this pi is equal to nothing but mi vi. So, this is nothing but mi vi square. Okay. So, we have this time derivative of the virial gives you two expressions on the right, that is Fi dot ri and mi vi square. Now, this is a simple term which is nothing but twice of the kinetic energy, and we will not worry too much about it till we arrive at the last stage. And so, we will this as a kinetic energy, and at times is also written with a T. Okay. In some books they write it with a T, but they mean the same thing. So, now consider a two body interaction. And in fact, it is very important to understand that anything larger than two bodies, it is very difficult to handle, and most of the time it is not possible to handle three body interactions. And so, ideally whenever we talk about interacting systems, which we will do towards the end, it is always a two body interaction, either it is two particle interacting via Coulomb interaction, or there are two spins which are interacting via some Ising or Heisenberg kind of interaction. Anything larger than that is difficult to handle, though there are spin systems we talk about Jalicinski-Muria, which is like a three body interaction, or there are other in other things there are ways to handle this, but it is not very common one, and secondly it is most of the time they are not relevant. So, we stick to a two body interaction, and let us talk about a gravitational interaction, which now we will talk about this two body interaction as some Fij, and understanding that it is the force on ith particle due to j. due to jth particle. So, the first term can be written as sum over I from 1 to n, and this is there is another sum from j which is not equal to I, and there is a f I j dotted with r I. Okay. So, now what I do is that I sort of consider that there are two body interaction. We write interaction, but here we are writing it as a force. So, which means that this two body interaction gives rise to a force, and most likely for a conservative case this force and interaction are related by a negative gradient, that is force is equal to negative gradient of a potential. And so, this is a two body force in that sense. So, which is what we have written here, and this f I j dot r I. So, we will have to, this j has to be anything but I, which means that it is different than I, and because a body cannot interact with itself, at least in this sense. Okay. So, this is say for example, and we are really doing it for a gravitational force. Okay. So, this f I j is a gravitational force. So, this is the assumption that we have in this present case, and so this j not equal to I think is clear, but then we can write this term as sum over I from 1 to n, and this is j less than I f I j dot r I, and another term which is I equal to 1 to n j greater than I f I j dot r I. I think it is clear because j is not equal to I. So, I take all the j's which are less than I as this term, and all the j's which are greater than I as this term, and let me write this as a and b terms. These are a and b. It is quite obvious that f I j is a n cross n matrix. For all I and j to run from 1 to n. Okay. So, we can write this as this is your say n cross n matrix, and we write I in this direction and we write j in this direction. So, if you write down the diagonal, so this f I j will not have any diagonal elements where I equal to j, because a particle cannot interact or cannot exert a force on itself. So, we have all these terms which are the first term, which are j less than I, would be represented in the lower diagonal, that is the lower block in the lower to the diagonal, and this is in the upper diagonal. So, b is a term that represents upper diagonal, and where j is greater than I. Okay. So, once we have written this down, let us work with this b term, which is I mean you can work with either, but we will just take b for example and then manipulate it and write it such that it looks similar to a and can be combined in some sense. Let me see how we can do that. So, there is a I from 1 to n, and now this is like a f I j sum over j which is greater than I and dotted with r I. Now, what I do is there is a crucial step. I interchange the I and j indices. Okay. This does not cause any harm to the discussion that we are undertaking. The reason is that these i's and j's are all dummy indices. So, we can write this as in the sense that I can still write it as I equal to 1 to n, and I write a j less than I, and I can write it as a f j I and then dotted with r I. So, we have what we have done is that interchanging I and j, and because of that the j greater than 1 term has now been written as j greater than I term is written as j less than I. Okay. Just a small manipulation that is done. Now, you see that Newton's third law comes into picture, which says that f I j equal to minus f j I. Okay. So, this equal and opposite force acting on a pair of bodies, and then my B can be written as sum over 1 to n j less than I and f I j dotted with R j. Okay. Let me see whether there is a mistake that I have made. This should be j, because I have changed R and I and j. All right. Sorry about that. So, this is equal to minus f I j R j. Now, I can combine A and B, which gives me this f I dot R I, which is one term in the derivative of the virial. This is equal to f I dot R I equal to, which was like A plus B. Now, this is like a sum over I equal to 1 to n j less than I for both the terms. I have a f I j dot R I and a minus sum over I equal to 1 to n and a j less than I f I j dot R j, and I can now combine the two terms and write this down as the first term is I from 1 to n. So, whether you write I to be equal to j, it really does not matter. I mean, in the sense that both these are dummy indices, they both go from 1 to n, with the only constraint that they are not this j is not equal to I, and so it is either greater than I or less than I. That is why this sum in B, which appears here, we do not change this this index that you see here. So, this still remains as I. So, I will write it here. Okay. So, once we get this, then we can just combine both the terms, which is I equal to 1 to n j less than I for both the terms, and I have f I j for both the terms, and this is R I minus R j. Now, you can introduce the shorthand notation where you write R I j equal to R I minus R j. In all the gravitational problems or electromagnetic problems, this notation is used. So, I can write this as I equal to 1 to n j less than I f I j and R I j vector, okay, where R I j is a vector that connects I and j. Now, take f I j to be equal to the gravitational force. Okay. So, f I j to be equal to g m I m j divided by R I j cube R I j vector. This is a usual form that you all are familiar with, this Newton's law of gravitation, where two masses m I and m j they experience a force among them as g m I m j divided by R I j cube, and this the force takes place in a direction this line joining from A to I to j. Okay. All right. So, we can go back to our original term, which is f I dot R I. This is equal to nothing but minus g this m I m j divided by R I j cube and then there is a Rij dot Rij, right, because this Ri is now this is equal to Fij dot Rij. So, Fij is this, now there will another Rij, so that makes it Rij square. Now, this will cancel and I get what I get is I get a term which is equal to the potential. So, this is the potential and this can be written as I equal to 1 to n, and there is j that is less than I, and this is nothing but equal to Vij. Okay. And so, this is the term that we have, and along with that we also have a potential energy. Okay. So, this is Ri minus Rj, and so there is a term, so this is Ri minus Rj, that is fine. So, this is that Rij equal to Ri minus Rj, and we have this potential term as this, and so your dq dt, that is time derivative of the virial, is now the total potential energy plus twice the kinetic energy, that is what we have derived. So, this is dq dt, and the theorem demands for long times the time average of dq dt is equal to 0. Okay. So, what we mean is that so if you have a dq dt average which is nothing but 1 over t 0 to t dq dt dt, this should be equal to 0 for t large. Okay. Ideally means t going to infinity. What I mean is that the equilibrium value of this derivative of the virial has to vanish, and that is what the theorem demands. Okay. So, if that is true, then we have if we take the derivative not derivative, but the average over long times. So, this is equal to 2 k equal to 0, and that gives us a very important result, that V is equal to minus of 2 k. And this is a result that is valid for the gravitational force. Now, this result does not hold good for other interaction terms. Now, if you need to find it for other interaction terms such as, so this is 1 over r, or this can be written as a k is equal to minus half of V. Okay. And for other interactions, say for example, what will it be for say the harmonic oscillator, or is it really valid for only for interacting systems, or it is also valid for non-interacting systems. We will see this result, but before that we just want to make a few comments. The comment is that this is so these are comments. One is that the result is shown for gravitational field or gravitational force or gravitational interaction, let us call it a gravitational interaction, but true for all other interactions. So, we state a simple result without a proof, that actually if you have a V going as some constant into some r to the power alpha, then the relationship between k and V is alpha by 2 into, so k is equal to average value of k equal to alpha by 2 into V. See here alpha equal to minus 1. So we got it as k equal to minus half of v, and so if you have v is equal to say r to the power square, which is the case for harmonic oscillator, in that case we will have a k to be equal to v, and this is another known problem in classical mechanics, that the average value of kinetic energy and the average value of potential energy is they are same. And in fact, this is also the statement of equipartition theorem, because equipartition theorem says that energy is equally partitioned at a given temperature T at equilibrium between all the harmonic degrees of freedom. So, you have one harmonic degree of freedom as the kinetic energy, which is p square, and the other harmonic degree of freedom is the potential energy, which goes as x square or r square, and so there this thing should be valid as well. Okay. So, this is one comment, and then second comment is that results are equally valid for classical and quantum physics, which means that if you want to go to hydrogen atom, and where the potential is again V equal to C divided by R, the Coulomb potential between the electron in the outermost orbit and the nucleus which contains a proton. So, this is of the form, so there is a minus sign there. We have ignored this minus sign, but we just interested with this dependence of V and on the positional coordinate or the configurational coordinates. So, this is C over R. So, we have the same result as the, so this for hydrogen atom. So, this k is equal to minus half of V, again as you have for this this harmonic oscillator, and this result is again same as the gravitational object, and it should be because the nature of the potential is this inverse 1 over r, or the force is inverse square law. Okay. Now, just imagine for a moment, I mean, if you have to calculate the expectation value of the kinetic energy between any arbitrary state of the hydrogen atom, which contains a log-ware polynomial and these exponential minus alpha r kind of term, and then trying to do this would require you to do a lot of mathematics in order to get this values, but we without doing any calculation we have this k equal to minus half of V, and also k plus V is equal to the energy of the system, which in this case is minus 13.6 by n square. Okay. So, we have this relation between k and V, and we also have another relation between k and V. So, we can calculate these values, these expectation values of kinetic and potential energies without any problem. All right. So, these two are the comments about this Virial theorem. Now, let us go to statistical mechanics. Not that all these things that we have said are not valid, but we just want to go to a classical gas or go to an oscillator, which are systems that we have been considering extensively for this course. Okay. So, what is the definition of virial? Once again, will the definition of virial would not vary, but however written with a different notation. So, this is equal to the Ri, and this is the force that you see, which is Pi dot, and the expectation value of this is called as a virial. So, it is the expectation value of the sum of the products of products of Qi, which are the configurational coordinates, and the forces acting on the system, Pi dot, which means the forces acting on particles of the system. All right. So, this is the definition of that, and now this from the equipartition theorem we know that this is really, let me do it one more time, but let me just state the result. So, this is Qi Pi dot minus 3 nkt. I have not written it in this form, but I will do it. So, let me do it here in this particular form, that. So, that will require me to derive. So, this is nothing but the equipartition theorem. This will need me to derive the equipartition theorem in terms of the virial. Okay. So, let us in a simple case, let us consider the Hamiltonian of the system to be a function of the Q and P, okay, which are written earlier, and then you consider what is the average value of this and x j. Now, you might wonder this from Q and P I am going to x I and x j. So, x I and x j can be any of the 6 n coordinates. What I mean is that they may not only be the positional coordinates or the configurational coordinates, they can also be the momenta coordinates. So, these x I and x j can take values anything between q 1 to q 3 n and p 1 to p 3 n. Okay. So, that is the understanding, and if we want to calculate the expectation value of this, we know that in the classical statistical mechanics we are going to weight it with the Boltzmann factor. So, this is nothing but the expectation value of this quantity is minus infinity to plus infinity, and all these x I del h del x j e to the power minus beta h. H is the Hamiltonian, it is written here, do not mix it up with magnetic field, which is not present here anyway. So, this is a d cube q 1 to d cube q n, just doing it in one dimension for simplicity, but it can be just written as in 3 dimension as well. So, d cube p n, and divided by an integral of this exponential minus beta h, and then you write the same thing d cube q 1 all the way up to d cube q n, and d cube p 1 equal to d cube p n. Okay. So, we write it in 1D, but really it can be, if you write it as 3n, it will just go over to the 3 dimension. So, once again we have to perform this integral that is there specifically on the numerator, and the way we do it is that we use integration by parts. And what do you take as first function and second function? So, you take the first function as x I and the second function v as del h del x j exponential minus beta h. So, this is the first function, and this is the second function. And what is the formula that we use there? So, we use u v dx is equal to u integral v dx minus du dx integral v dx whole dx. Okay. So, now you have identified what is u and what is b, sorry v, and then we can do this quantity which is equal to xi del h del xj. This would give us, so the we are just simply doing the integral of the numerator. So, the denominator is not important, because the denominator would give us equal to 1, because that is a normalized probability for a system, I mean with beta as 1 over t or kt, that is a normalized probability. So, we simply need to calculate this quantity, the numerator. So, this is minus infinity to plus infinity, and we have 1 over beta with a minus sign here. Please do it carefully and you should get this result, and e to the power minus beta h. So, that is your integral v dx, and this is from x j equal to minus infinity to x j variable to be plus infinity, okay, and plus 1 over beta, and there is a del xi del xj, that is the second term, and there is a e to the power minus beta h dxj, and then what we do is that we will write it as d cube qj d cube pj. Now, I will write a prime here and a prime here, with the understanding that the dxj is not included. So, dxj, that coordinate is not included, and once again I remind you that dxj, the xj coordinate does not necessarily mean that we are talking about positional coordinate. We can talk about it as a momentum coordinate also. So, any of the p1 to pn, it could be there. We will just see it in a moment that this xj is just a dummy index. So, dxj is excluded from this integral, because you have already written a dxj inside this square bracket. Now, you see the first term really goes to 0, because at the extremum coordinates of the Hamiltonian really becomes very large. Okay. So, the Hamiltonian diverges at these plus infinity and minus infinity of one of the coordinates, because this h is a function of p and q. So, this xj can be either p or q, and this goes to 0 because of that, because exponential minus beta h goes to 0. So, we are left with one term only, and this term is nothing but delta ij. So, you are taking a derivative of xi with respect to xj, and unless I equal to j, this would vanish. So, we are left with a term, this is equal to 1 over beta delta ij, and then of course, all these terms which are exponential beta h d cube q1 to d cube qn and d cube p1 to d cube pn. Now, your dxj is included. So, all coordinates are included. And this is nothing but equal to 1. This whole thing is equal to 1, because it is a normalized probability. So, what we get for this expectation value, this is simply nothing but equal to 1 over beta. So, xi del h del xj is nothing but equal to 1 over beta delta ij, which is equal to delta ij into kt, and so this is the result that we get for this virial. And now, let us take xi equal to xj. So, case 1, xi equal to xj equal to pi, that is all these coordinates are xi and xj both are all are momentum coordinates. So, then we can write it as pi del h del pi is equal to pi, and del h del pi, as you know, is equal to qi dot. So, this is equal to kt, okay, because we have taken I equal to j. Case 2, so xi and xj both are equal to qi. So, we have qi del h del qi, this is equal to qi, and del h del qi is minus pi dot. So, this is pi dot, this is equal to kt once again. Now, you see this is the virial that you have seen earlier, that is a sum over I from 1 to 3n, and you have 3n, and this is like fi dot ri. Okay, that is the virial that we have been talking about when we talked about or discussed this gravitating bodies. So, if you go over to 3 dimension, this means that we will have, so let me write it here, in 3D we can do it, and we can get this sum over I pi del h del pi equal to, it is writing it once again, yes, I mean this thing should have been inside. So, this is inside. So, this is equal to pi qi dot, which is equal to 3n kt, and similarly you have sum over I qi del h del qi, this is equal to minus of qi pi dot and this is equal to 3n kt once again. So, that tells that each harmonic degree of freedom gives you this nkt, the 2 harmonic degrees of freedom, p square plus q square, because h is explicitly taken as a function of q and p, and so this equipartition theorem is proved using using virial. Okay. So, that tells us that they are consistent with each other, and we get these nice results that the energy is equally partitioned between each harmonic degree of freedom. It is one of the cornerstone results in statistical mechanics. Let me do it for a gas, classical ideal gas. And that tells us that you can write this again, as I said, that so you see that here what we have written without a proof, that qi pi dot equal to minus 3n kt, that is proved here, is equal to qi pi dot sum over I is equal to minus 3n kt. Okay. So, once again, as I said, that use this as a virial, definition of a virial, which is nothing but qi fi, and this is equal to, now this fi is nothing but equal to p ds, or ds is the area. So, for a gas which is enclosed in a container, so this is the piston that you have, and so there is a gas there. So, the force that is there is entirely due to the pressure, and this pressure is nothing but so the force is equal to minus P ds, and the reason that we have written a minus sign is that the P is acting downward here, and so that's the pressure due to the piston, and ds, which is the surface area, that's acting upward. And so we have there is this sign, mutual sign between them, and this is equal to minus P, and then there is a S, and then there is a R dot ds. So, R is nothing but Qi, and F is written as P ds, and so on. So, R is the position vector of the particles in the gas, which are in the vicinity of the wells that you see. Okay. So, this is nothing but equal to minus P, and we can, P is the pressure. Okay. So, this is the pressure, as we said. Now, this we can use a divergence theorem to convert it into a divergence of R dV. Okay. And divergence of R is nothing but 3, because in 3 spatial direction we can write it as I ddx plus I cap ddx plus I cap ddy, or you can write it as del del y, j cap del del y, and k cap dd del del z, dotted with x I cap plus y j cap plus z k cap, and this is nothing but equal to 3. So, this is equal to 3. Okay. So, this becomes equal to minus 3 PV. So, virial for a classical ideal gas, virial PV. Okay. And if we use this relation, the one that is here, here the last relation, where we have taken H to be only a function of Q, or rather only a function of one coordinate, not it may not be Q. I mean, in this particular case, it is a P, that is momentum. So, if we compare between the two, we get a minus 3 PV equal to minus 3 NKT, and then we get this as the PV equal to NKT, which is the equation of state for the gas. Okay. And the internal energy is of course purely kinetic, and the virial is nothing but equal to minus 2 the kinetic energy. So, this purely kinetic. So, we are talking about classical ideal gas, there is no interaction between them. So, what we have done is that we have derived two very important theorems in statistical mechanics, the equipartition theorem and the virial theorem. The equipartition theorem says at an equilibrium temperature T, how the energy is partitioned between various harmonic degrees of freedom, and it says that it is equally partitioned. Okay. And hence we have done a virial theorem which establishes a relationship between the average kinetic energy and average potential energy, and is equally valid for an interacting system, a pairwise interacting system, which we are mostly familiar with. In that context, we have shown this result to be valid for this gravitational system, and then you can also write it for the harmonic oscillator and get this this relationship between the average value of V and the average kinetic energy. And we have explained that how this result can be very useful in determining the relationship between the average quantities, average energies in a quantum mechanical system, where a general wave function for the say the nth state or nth wave function of the electron in a hydrogen atom can be quite complicated in terms of its polynomials and multiplied by some exponential functions or even in harmonic oscillator. But this theorem, that is a Virial theorem, gives you a very nice and crisp relationship between k and v, or t and v, if you like to call it. All right. So, let us go over to Grand Canonical Distribution. Or Grand Canonical Ensemble. The way it is different than the canonical ensemble is the following. Just like energy was not a measurable quantity and we have allowed the system, our system, to exchange energies with the surrounding and come to an equilibrium, number of particles of a system is again not a measurable quantity. And let us allow this flexibility of our system to exchange number of particles with the other members of the ensemble and come to an equilibrium, say now not temperature has already, of course, it comes to an equilibrium temperature, but there has to be another equilibrium quantity that should be established between our system and the surrounding, and this is called as a chemical potential. So, now we will draw the same picture that we have drawn earlier. We have our system to be some A, and this is to be A prime, and this the whole system is A 0, which is of course isolated, and this is characterized by energy E r, or say just use this thing that it's energy E s and number of particles to be N r. And so this let us write it as E s and N r. So, which means that our system has N r number of particles which are occupying this E s energy level, whereas the A prime that has E s prime and N r prime. Okay. And again E s is much smaller than E s prime, or the total E 0 of the system. E 0 is the total energy of A 0, and N 0, say for example, is the total number of particles that is there, which is again a constant. So, what we write is that we write N r plus N r prime is equal to a constant which is say N 0, and we have to write that E r plus E r prime is again equal to E 0, and both are constants. Remember, the first condition was not there in the canonical ensemble. Okay. N r is of course a particular value for these system to occupy, our system to occupy this N r number of particles in a given energy level E r. So, this is, so you can write this thing as E s and E s prime, because we are using two different symbols, one characterizing the number of particles, other characterizing the energy of the system. Okay. And once again these N r over N 0 is equal to 1 minus N r prime by N 0, which is much smaller than 1, which we have seen earlier, and E s over E 0 is 1 minus E s prime over E 0, which is again much smaller than 1. We will not do an entire derivation, but the derivation follows exactly along the same lines as the canonical ensemble, and you can rerun this derivation now with an additional Lagrange's undetermined multiplier, which will introduce, which is called as a chemical potential, or the mu. Okay. So, we ask this question that what is the probability that the system of mine or system of ours, which has N r number of particles, occupies an energy state E s among all the possible available energy states of the problem. Now, in order to do that, we will have to consider the number of microstates that are present, that can be available, or that are accessible for all the other members of the ensemble to be distributed between these energy levels E s prime and this nr prime being the number of particles. Okay. The probability is P r s, which is proportional to the omega prime nr prime E s prime. Okay. This has been explained thoroughly when we did the canonical ensemble, why this probability has to depend upon the number of microstates of all other members of the ensemble excluding our system to occupy these various energy levels, because our system has only one microstate, and all the other microstates are equally available to all the different members of the ensemble. And because these events are independent, so we multiply 1 by this number, which is omega prime, which is for the system A prime to occupy nr number of particles among the available E s prime systems. So, what we do is this is proportional to omega prime and n 0 minus nr and E 0 minus E s. So, in order to find this probability, what we do is that we take the log of this and expand it about n 0 and E 0, which are constant quantities. So, we do a log of P r s, this is equal to a log of omega prime n 0 minus nr E 0 minus E s, write it clearly, E 0 minus E s, and this is equal to, if you expand it, it's log of omega prime. So, we do a Taylor expansion. And to remind you, what is Taylor expansion? Taylor expansion is f of x expanded about x 0, the first term is constant, and then you have a df dx or del f del x. Here we are talking about one variable, so it's okay to write this, and then of course there is half and d2f dx2 x at x 0 x minus x 0 square, and this. So, depending upon situations, we either chop off the expansion at the first term, that is after the constant term, or in some cases where we are talking about equilibrium, then we sort of go over to the second term as well. Here it is okay to chop it off at the first term. So, this is n 0 E 0 and plus del ln omega prime del n prime, this is evaluated at n prime equal to n 0 and minus nr. So, this is that x minus x 0. So, this is nr, and there is another term which is del ln omega prime del E prime evaluated at E prime equal to E 0, and we have a minus E s. Okay. So, E prime equal to E 0 and so on. So, this is equal to minus into minus E s. So, it is exactly the same thing. Apart from that, there are two terms now which are variable, both n and e, and this is nothing but equal to, so this log of this P r s, I hope I have written it as P r s, yes, P r s. So, log of P r s is nothing but equal to, if we are writing it almost equal to, because we have ignored the terms that are higher order. So, it is a log of omega prime n 0 E 0, which is of course a constant, and then there is a mu divided by k t prime, mu prime k t prime minus E s over k t prime. where we have defined already beta equal to del ln omega del E is a very familiar definition, which is in terms of the entropy, which is equal to minus 1 over kT. You write this evaluated at this E prime equal to E0, like n prime equal to n0 and E prime equal to E0. So, this E prime equal to E0, and of course, we also have a minus mu over kT, which is nothing but minus beta mu, that is equal to del ln omega del n evaluated at n prime equal to n0. So, we now have a constant term which does not make too much of difference. It will just when we want to calculate PRS, it will just be a constant, and this constant would be absorbed when we define the total probability to be equal to 1. So, the log of PRS is like this. So, at equilibrium, it is important to understand that there is no mu prime and T prime separately. We have the system, our system will come to an equilibrium chemical potential mu prime equal to mu and T prime equal to T, which means that, or we write it T prime equal to T. So, which means beta prime equal to beta. So, if that is true, then we have a log of omega prime E S prime n r prime is equal to log of omega prime n 0 E 0 and plus mu over kT minus E S over kT. Okay. So, there is a nr here which I have forgotten. So, there is a nr here, and so this gives us that PRS has this Boltzmann form, or it is proportional to e to the power minus alpha nr minus beta ES, and in a normalized form we can write it as PRS is equal to exponential minus alpha nr and beta ES and divided by sum over RS exponential minus alpha nr minus beta ES, where of course your alpha is equal to minus mu over kT and beta equal to 1 over kT. Okay. So, these are the two Lagrange's undetermined multiplier required for the constancy of the total energy and the total number of particles. So, you are allowed to assign a particular number of particles to a given energy state, but while assigning you also have to follow that the total energy and the total number of particle to be constant. So, this is the the sort of distribution for the Grand Canonical Ensemble. It is almost same as the canonical ensemble, excepting that we also have inside the argument of the exponential, we have a term which contains a mu. Okay. And if we want to know that how is this like this quantity which we have done earlier NRS, that is how is this distribution, how does this distribution look like, that is assignment of particles in different energy levels. And from our experience we know that this distribution, which is nothing but equal to some n factorial divided by this product of RS and NRS factorial, this gives you the the various number of ways that you can distribute NR particles in ES energy states, and this distribution is not really a flat or a broad distribution. We know that in order to have the experimental quantities as they say the pressure, volume and temperature, this is really sharply peaked, and that NRS, the most probable NRS for the thermodynamic limit. So, n going to infinity divided by n, it gives you this NRS star divided by n, again limit n going to infinity. This is nothing but the same distribution that we just saw, minus alpha NR minus beta ES and divided by sum over R and S exponential minus alpha NR minus beta ES. I hope you appreciate that that there are enormously large number of ways to distribute a number of particles, certain number of particles in certain energy levels. However, among these enormously large number of possibilities, there are only the average possibility is same as the most probable possibility, which are given here because the average value of NRS is same as this NRS star. We have not done this derivation here, but we have done the derivation while we discussed canonical distribution, but the same, as I said, everything else follows through. This gives you the distribution to be sharply peaked, and these distributions are very important for us. We just write down the average number of particles and average energy, and end here this discussion, and will of course carry on with some examples of the Grand Canonical. So, now you see that you are allowed to exchange number of particles between your system and the surroundings, or each of the members of the ensemble of the surrounding, they can also exchange energy and number of particles. We still should be able to define average energy and average number of particles. This is an important sort of understanding or concept that we need to imbibe here. So, this n is equal to R S NR exponential minus alpha NR minus beta ES, and this is divided by sum over RS exponential this probability, of course, this Boltzmann probability. Just a definition, stick to the basic definition that you are trying to calculate the average value of a quantity. You weight it by its weight, statistical weight, which is here the Boltzmann term, and then you divide it by the total probability, which is of course equal to 1. So, this is equal to minus del alpha of these log of this R S exponential minus alpha NR minus beta ES, and so this is that partition function. So, we will define this later as a Grand Canonical partition function. Just wait till we arrive at the next class for this. So, this is again R and S, and E S just exponential minus alpha NR minus beta ES divided by R S exponential minus alpha NR minus beta ES, which also shares a similar relationship as the average number of particles. So, this average energy, and this is equal to log of sum over Rs and exponential minus alpha nr minus beta Es, and we just mentioned that this quantity now will be called as the Grand Canonical partition function. So, this is equal to this sum over Rs exponential minus alpha nr minus beta Es, and of course, alpha is equal to minus mu over kT and beta equal to 1 over kT. Okay. And just like what we have done for the canonical distribution, we will use it in order to find or rather the kT log z will be related to a potential which we will call as a grand potential, and this G is for the grand canonical. Okay. We will use this terminology and then we will use that in order to calculate various quantities that we are familiar with. So, we shall stop here and carry on with more discussions on the Grand Canonical Ensemble. Thank you.